Okay, so welcome back, everybody. We had begun our study of 18th century mathematicians. So I'd presented a list last time of the ones that we were going to focus on. For now, there will be a couple others that we talk about, but this will be the main list that we'll focus on. For now, the results of the poll show that it is almost exactly evenly split. Hold on one second. My cats are fighting. Let me break them up. Okay. So the poll results are almost evenly split exactly, and so I guess I'll just try to kind of pick some of the more interesting and accessible topics from those three. Just kind of try to provide a nice broad selection and hit most of the big names and many of the very huge contributions in those areas. So anyway, so last time I had mentioned Brooke-Taylor and the Taylor series. The main importance of the Taylor series was that for any reasonable function, so if f is a reasonable function, then we could write f as a Taylor series. Okay, and so you might say, well, here you've like shifted f by this a, right? But I want to write like f of x, right, the function that I'm starting with. I want to write f of x itself as a power series. And the reason I said last time that you would maybe want to do that is because really what a power series is, and what the Taylor series is an infinite degree polynomial. It's like a polynomial that doesn't have a highest power necessarily. It just continues on indefinitely. And so what is nice, though, is that the things that you might want to do with this function that depend on a computation that you need to do term by term, right? So things like taking a derivative or taking an integral, right? These fundamental operations of calculus. Well, it turns out that both of those operations are linear, meaning that they split up across sums and you can pull constants through them. Okay, and so what that means is that a polynomial type thing is absolutely perfect to deal with for derivatives and integrals. So, for instance, if I want to, do some kind of calculation, I could do it term by term and then sum the results, right? That's the idea. And that's why a polynomial-like thing is very nice. Polynomials are basically the nicest functions that we know. So being able to take a function that is very much not a polynomial, okay, so a function is very much not, at least on its face, anything like a polynomial, and being able to say, hey, there is this expression, this Taylor series, right, for some of these functions, that that allows us to think of that function as, an infinite degree polynomial, as an almost polynomial-like thing. It's very nice. Okay, it's very useful. Okay. But to address this concern you have that this is a way of writing f of a plus x as this series, if you want to write f of x, f of x itself as this same series, you just need to set a equal to 0. So this is exactly what Mclaren did, and the Mclaren series is named after this. So Mclaren set a equal to 0. Now, Mclaren discovered this separately. He didn't just literally set a equal to 0. He discovered the Mclaren series separately, but this is the a equals 0 case of the Taylor series. And so if we're looking at this, if we set a equal to 0 here, I have f of x is equal to f of 0 plus x times f prime of 0 plus x squared times f double prime of 0 over 2 factorial and so on, right? So this becomes f of x is equal to f of 0 plus x times f prime of 0 plus x squared times f double prime of 0 over 2 factorial, and so on, rewriting it using summation notation. This is the sum from n equals 0 to infinity of the nth derivative of f evaluated at 0 over n factorial x to the n. This is the Mclaren series. Okay, so this is named after Colin Mclaren, who's a Scotsman. Okay, he treated this special case, a equals 0. This was done in a work called the Treatise of Fluxions, okay, using Newton's term for derivatives. Okay, so this is where this was worked out. So this was done in 1742, I think. That's when this was published. He tried to actually address these complaints that had been risen by George Berkeley about infinitesimals and how it was not on rigorous footing. But Mclaren actually wasn't even able to show the conditions that would say that this Mclaren series converged. Right. So neither Taylor nor Mclaren understood a proper notion of convergence. Again, as I said, that wouldn't come until much later. That wouldn't come until like near the end of the 1800s is when these things began to be understood properly. Okay. Okay. Another name that I mentioned in my list that is known primarily for a single fact. So this is Abraham de Moivres, who is known for a formula, de Moivres Formula. So he was born in France but lived in England for most of his life. He is known for de Moivres Formula, which is the following. If you say I is your imaginary unit, so I is square root of -1, then the cosine of x plus I times sine of x raised to the nth power is equal to cosine of nx plus I sine of nx. Now, you can prove this, so you need to do some algebra involving the imaginary unit I. The main thing to know about it, right, is it's not a real number. It is a number such that it's when you square it, you get -1. Right, so I squared is -1. I'll rewrite that over here since I kind of ran out of room there. So I squared is -1. So if you add in an I, you want to do algebra with it, and you want it to satisfy, you want arithmetic with I to satisfy all the nice things that, say, multiplication and addition of real numbers satisfies, right? Then basically the only thing you need to specify is this is how I behaves, so it's not a real number, but I squared is -1, and then you can work out the algebra of how this works. So we'll go over maybe the complex numbers more in detail later when I get to the special topics portion where I'm trying to cover a bunch of different stuff. But for now, that's what I'll say. So one thing, you can prove this just purely via algebra, which I believe is what was done here, using induction. You can prove this really easily via something called polar form of a complex number. So this is like really, really easy to show during or using the polar form of a complex number. This also leads to some particularly, or I should say, a special case of this. Once you start dealing with quantities that look like this, and this involves what's called polar form, which is very closely related to polar coordinates. If you've seen polar coordinates, it's essentially polar coordinates just represented by a complex number instead in a very particular way. Once you've seen that, there's a lot of these nice formulas that you may have come across before that kind of immediately pop out. So de Moivre is only known for this because he was a very unlucky guy. So whenever you're feeling down on your luck, you should think about de Moivre and realize that some people really get it hard. So de Moivre had recommendations from both Newton and Leibniz. Okay, so he had letters of recommendations from Newton and Leibniz. Okay, so he's going. Imagine you're going to apply to grad school, right? And you two of your recommenders are Newton and Leibniz. Okay, and then imagine not getting in anywhere. Right, that you apply, because that's what happened to de Moivre. He never got a full-time job as a professional mathematician, despite, like I said, high recommendation from both Newton and Leibniz. He was passed over and never got a mathematics job. He basically made his living either through private tutoring for wealthy families or answering gamblers' problems concerning probability. So gamblers would send him questions about probability involving various types of poker and card games, various different types of gambling scenarios, and he would answer their questions for a price, and that was how he supported himself. Which, is pretty neat, but definitely a real shame that he didn't get more of an opportunity. So since the Taylor series is infinite, how would you sum the polynomials? Ben, that's a good question, and exactly that problem is what I'm going to talk about here in a second. So power series are like more complicated examples of just series, because they're series that you're plugging in different values of x here. So I'm gonna talk a little bit about series. I've only mentioned them a little bit before. I mentioned, I think I mentioned the harmonic series already, but I'm going to, if I didn't, then I'm gonna do it here in a few minutes. So anyway, the legend about de Moivre is that as he got older, he decided to sleep 15 minutes longer every day, and then when he finally reached the full 24 hours, he died. So that's the story of de Moivre. So next, this is getting me set up to talk about Euler, and this is going to be a long topic. This is probably going to bleed into next lecture too, and that's still not going to cover it. So Leonhard Euler, he was a Swiss mathematician. So he was Swiss. In fact, I think Euler, I know that Gauss has been on some printing of the euro, and I think Euler has as well. Anyway, so Euler was Swiss, and though he spent most of his professional life in St. Petersburg, so though he spent a decent portion of his life, early life in Berlin, and most of his life in St. Petersburg. So he spent most of his life in St. Petersburg. He eventually went blind later in life, though this apparently did not really slow his math output at all, and he continued publishing, being more or less completely blind until he died. And that it was pretty amazing to keep up with that pace, because he's the most prolific mathematician of all time. He has literally published more than basically any mathematician. There's only a couple other mathematicians that are arguably anywhere near him as far as being that productive. So arguably the most prolific mathematician of all time. So if all of his mathematical works were put into like a giant, collection of volumes, it would span a ridiculous length. It would be huge. And Euler is he is kind of in terms of his mathematical contributions, it's kind of hard to overstate exactly how much he contributed to, and in areas that were wide-ranging. So the problem is, up until now, the sorts of math being done, you had geometry, and then eventually, so you had geometry, and then you had early algebra, but like Babylonian style algebra, right? Which wouldn't really be improved upon as far as the theory of equations goes until Diophantus. And then after Diophantus, this didn't get improved upon until, much later, until you get Indian and Islamic mathematicians, in like the 11 and 1200s. And then eventually, right, Renaissance mathematicians, so Tartaglia and Cardano, and Ferrari, that was the big step in algebra. But those were kind of the two main fields of mathematics that interacted. And then, of course, we had, with some of this last batch of mathematicians I talked about, kind of the birth of probability, right? With so Fermat, Fermat and Pascal were kind of some of the first to do work on probability, and a little bit more was done by the mathematicians in the 1600s. But that was pretty much it in terms of trying to classify what type of math was being done. There wasn't a whole lot of options. It was basically geometry, algebra, and then the very, very basic stuff in probability, and that was more or less it. So Euler is one of the first instances. Of course, with Newton and Leibniz, you had the discovery of calculus, and so we have like literally the birth of the field of analysis. So what we call analysis was birthed by calculus. It's kind of where calculus heads after the early work. So Euler is kind of the first mathematician that is doing work in mathematics all over all of those fields, and simultaneously discovering new fields. And substantially different and new, completely original and novel ideas in almost all of those fields simultaneously. So it's really, really impressive. Just to go through a few things, one that you are already aware of, almost certainly, is Eulers number. So Eulers number, I made a mess of writing this. So Eulers number E, right? The base of the natural logarithm. So the natural logarithm is the one originally. So this was, the original logarithm that we discussed just prior to our work with on Newton and Leibniz. So it's the same logarithm, and the base of that natural logarithm. So the original logarithm we talked about was base 1 over e. The natural log is base e, so this is the base of the natural logarithm. By definition, you can say that that's the logarithm with base e. How is e defined? There's a number of ways that you can define e, but e is defined as the limit as n goes to infinity of 1 plus 1 over n to the n, which, if you compute this, is approximately 2.718281828 8, 4, 5, 9, 0, and so on. Okay, we could do better, but I'll stop at the first 0. All right, so it is this irrational number. It turns out it is also transcendental. We'll talk a little bit about what that means and how that was proven earlier. I think I mentioned transcendental once, like a single time early in the semester. This is what this number is. It might seem strange that a number like this would be the thing that naturally pops up when you're computing that logarithm that we talked about, you know, that really, really like crude way of thinking about it as motion, right? Or in terms of motion along the x-axis. But no, this is exactly the number that pops up. You might recognize an expression like this as arising somewhere. Right? So can anyone watching tell me where they've seen some expression that looks like 1 plus 1 over n to the n? So this expression, right, there's certain things in the actual original expression that you would have to set to be 1 here. But recall compound interest. How do I compute compound interest? Right. So this rate of change, right, that I can view as a derivative is p times 1 plus r over n to the n times t, right? Where n is the number of times that you are compounding, right? So, for instance, if you're talking about compounding monthly, yearly, weekly, then n changes depending on your time scale, right? So, so this is the number of times that you are compounding. And also recall that if you have continuously compounded interest, what does this formula become? So periodic compounding is you compound at certain times. There's a finite number of times that this interest is compounded. So this is like a finite number of compounding is going on, right? But continuously compounded means that you're compounding as you go, right? Continuously, right? And so what is it that's going on here? Well, in that instance, to compute interest, right, I take a limit, and I take the limit as n goes to infinity, right? But the limit as n goes to infinity of this quantity, right, 1 plus 1 over n to the n, is e. And so what happens here is that this quantity becomes p times e to the RT. Okay. And this arises from this limit, okay? And so the reason why E crops up as this limit you could think of as being related to a limit that you take going from periodically compound interest to continuously compound interest. Okay. So that's one natural way of seeing where that limit shows up. But it turns out that this limit is E. Now, if you if you are wondering, like, why does it work out this way? This is one of the nice examples of when you're doing limits using Lhopitals Rule. So I haven't mentioned L'Hopital. I will throw his name in later. But Lhopitals Rule is a famous theorem that allows you to compute limits using a trick. And you can only use this trick under certain circumstances. The thing that you're trying to take the limit of has to be an indeterminate form. Okay. Well, it turns out this is one of those indeterminate form integrals, or sorry, limits. And the reason why is that you would be very tempted to look at this expression, and if you're trying to reason through what this expression should be, you would say, okay, well, as n is going to infinity, right, the quantity inside the parentheses here should be getting very, very close to 1, because this is 1 plus 1 over n. Right? And if n is getting very, very huge, then 1 plus 1 over a very, very huge number, that's basically 1 plus 0 here, right? So the quantity inside the parentheses here is getting very, very close to 1, right? Well, if it's getting very, very close to 1 as n goes to infinity, and we're raising that thing that's very, very close to 1 to a very, very large exponent, then you would be forgiven for thinking that this thing should be 1. Right? In fact, if we just plug in our n to be infinity, this becomes an example of an indeterminate form that is usually called 1 to the infinity. Right? This is like a real, real casual way of writing it. Okay. And now you might think 1 to the infinity, that should be 1, right? Well, this is considered an indeterminate form. It doesn't have to be 1. It could be something that's not 1. Okay, it could be e. In fact, in this case, it is e. It could be e squared. It could be e to the 5. Okay, it could be a number of things here. Okay, it could also be 5. It could be 7. It could be basically any number that you want it to be. Okay, now why, or any positive number that you want it to be. Now, why is that? Well, if you want to actually see this, convince yourself by picking a few huge values of n. So say we'll start with n equals 50. We'll start, so we'll pick n equals 50, then we'll do n equals 500, then 1,000, then 10,000. Pick all of those values and plug this into a calculator or a computer, and you'll see that already you're very, very close to the first few digits of this number. Okay, and so just computing this quantity when n is getting large, you see that you're getting very, very close to this quantity. All right. Okay. So Euler's number is named for Euler, although as we saw, this number was happened upon earlier in the context of logarithms, but Euler did a ton of computations with it, and he's also responsible for explicitly writing out that limit that I just wrote out. So this Euler's number is, of course, used in what's called polar form. So polar form of a complex number. I will go into more detail later about this, but the polar form of a complex number is a number that looks like a plus ib, where I is the imaginary unit, right, square root of minus 1, and a and b are real numbers. Okay. And so a plus ib is a complex number, but it turns out that if we call z this complex number a plus ib, there is a polar form of z. Okay, and that polar form is z is equal to r e to the I theta. Okay. Now, really, we're saying something different here. Okay. To see what it is that we're saying, I'm going to take a brief little detour. Okay. Let's go back to Taylor series. Okay. And I want to compute Taylor series for some functions that I know of that are not obvious polynomials, right? So I want to compute Taylor series for the functions e to the x, right? So that's my Eulers number e raised to the x, cosine x and sine x. I want to compute Taylor series for these. Okay, let me bring back my expression here. Oh, that's my Mclaren series. Where's my Taylor series? Well, actually, the Mclaren series is what I want to compute, so let's just use this. So to compute the Mclaren series, what I need to do are compute derivatives of varying orders. So compute first, second, third, fourth, fifth derivatives. So to compute those higher order derivatives, I just continuously take derivatives. Okay, and then I form the Mclaren series in this way by putting these over n factorial, where I'm taking the nth derivative here, right? So let's do this for e to the x. So let's let our function f of x be e to the x. Okay. So I want to compute a few quantities here. I want to compute the derivative f prime of x, and I'm in luck here because what is the derivative of e to the x? I'm not going to go through a derivation of why this is, but the derivative, the fluxion, right, of e to the x is itself. Okay. It's the only non-trivial function that is true for. Okay, so any other non-trivial function that this is true for is some constant times e to the x, right, or e to some constant times x. But e to the x specifically doesn't just keep the same form. It is literally, that is the same thing. It's its own derivative. And this is true. I continuously take derivatives. And of course, this is what I get. So I take the fourth derivative, that's still e to the x. Okay. So then evaluating these at 0, f prime of 0 is e to the 0, which is 1. But then all of these are 1 at 0. So f double prime at 0 is also 1. F triple prime of 0 is 1. And f quadruple prime of 0 is 1. F of 0 itself is also 1. And so, what is the Mclaren series of e to the x? So then the Mclaren series of e to the x is what? Well, just following the definition of the Mclaren series, it's the sum from n equals 0 to infinity of f, or the nth derivative of f evaluated at 0 over n factorial times x to the n. But we saw that all these are 1, right? So if I write this out, this would be 1, right? So this would be 1 plus 1. So this is at the 0th term, this is over 0 factorial, so it's f of 0, which is 1 over 1, which is 1. X to the 0 is also 1, so that's 1. Plus, this is going to be 1 over 1 factorial times x to the 1, plus 1 over 2 factorial times x squared, plus 1 over 3 factorial times x cubed, plus 1 over 4 factorial times x to the 4th, and so on. And so, e to the x can be thought of as the sum from n equals 0 to infinity of x to the n over n factorial. Or written out as a sum, this is 1 plus x plus x squared over 2 factorial, which is just 2, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, and so on. Now, this doesn't quite answer Benz's question of how do I sum these yet, Okay, but I'll get to that in a second. All right, and so we can talk about convergence, but the thing is that if this is going to be true, since we know e to the x is defined for every x, there's no problem plugging in any real number x you want to here. This thing had better converge for every x. So no matter what number x I plug in, I had better be able to sum this series. Okay, and it turns out that I can. So I had mentioned this previously, that this relies on computing something called the sequence of partial sums, and then computing that limit. And if that limit exists, then that is the sum. That is the sum of the series. Okay, but it turns out that summing series is it's very tricky. It's very complicated. So I will, and I'll talk about that here in a little bit. But this is e to the x. In fact, this is sometimes taken to be the definition of e to the x. So some people in some math books, Serge Lang wrote a graduate textbook on complex analysis, and it begins with this. And I think it begins basically saying that the exponential function e to the x is the most beautiful function in all of math. And here's its definition. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial. This is the most beautiful function in all of math. All right, so this is the most beautiful function in math. So why would this be called the most beautiful function in all of math? Well, it is in a way, so you might look at that and say, why wouldn't you take like a line, right? A linear function or a parabola or something like that. The thing about e to the x is that it is the only non-trivial function that is maximally simple when it comes to taking derivatives and integrals, right? It is its own derivative, it is its own integral. Okay, and so it is also like the basis of solving the very simplest differential equations are solved using the exponential function. Okay, now another thing is that it includes sitting inside it some other functions that you might not think about. Okay, so now I want to find the Mclaren series of sine and cosine. So I want to find the Mclaren series of sine x. How do I do that? Well, my function here is going to be sine x. So doing the same thing, I take derivatives. Well, the derivative of sine x is cosine x. And to take the double derivative of sine x, I take the derivative of the first derivative, so I'm taking the derivative of cosine x. The derivative of cosine x is minus sine x. Okay, the f triple prime is the derivative of the second derivative, so this is the derivative of minus sine x. That is minus cosine x. And finally, taking the fourth derivative, I'm taking the first derivative of the third derivative, so that's derivative of minus cosine x. That's minus sine x, so it's just sine x. So it repeats after that. Right? You take four derivatives in a row, and that takes you back to the thing you started with here. Okay. All right. So that's fine. That's interesting. Okay, now let's plug in 0 here. F of 0, that's sine 0, and that's 0. Okay, f prime of 0 is cosine 0, and that's 1. F double prime of 0 is minus sine 0, which is still 0. F triple prime of 0 is minus cosine 0, which is minus 1. And f quadruple prime of 0 is sine 0 again, which is 0, and this sequence repeats. Okay. So what is the Mclaren series of sine x? So sine x is, the 0th term is 0, so that's 0, plus the first order term is 1, times x, so that's plus x here. Okay, the next second order term is plus 0 over 2 factorial times x squared minus 1 over 3 factorial times x cubed. Right. The fourth is plus 0 over 4 factorial times x to the fourth plus 1 over 5 factorial, oh, I'm slightly off screen, times x to the fifth plus, or it doesn't matter whether it's plus or minus because I'm writing a 0 here, so it's plus 0 over 6 factorial times x to the sixth minus 1 over 7 factorial x to the seventh, and so on. Okay, so writing this out, getting rid of the zeros, what do I have here? Well, the Mclaren Series expansion of sine x is going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. So I want you to compare that to what's written here. Right? How are they related? Well, I have this alternating sign business, right? So there's some minus signs in here. But also notice that this only contains the odd powers, right? Whereas e to the x contains all the powers. Okay. Let's do another one. Let's do cosine x. Okay, so f of x is cosine x. So what is f prime of x? Well, my derivative of cosine x is minus sine x. And my second derivative, that is my first derivative of the first derivative, of minus sine x is minus cosine x. And f triple prime of x is, so derivative of minus cosine x is minus sine x, so this is sine x. And my quadruple derivative of x then is first derivative of third derivative, so it's a derivative of sine x, which is just cosine x, so I'm back again to cosine x, and it repeats after that. Okay, let's plug in 0 here, so f of 0 is cosine 0, which is 1. And f prime of 0 is minus sine 0, that's just 0. And f double prime of 0 is minus cosine 0, which is minus 1. And f triple prime of 0 is sine 0, which is 0. And f quadruple prime of 0 is 1. And then it repeats after that. So then writing out the Mclaren series, cosine x is... here I'm going to have the 0th term, so this is 1 plus the first order term is now zeroed out, so my first is going to be minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus, and so on. Again, compare that here. Okay. All right, we're almost there. All right, so comparing this again, maybe I should point it out. What does this contain? So the 1 is there. Forgetting about the alternating signs for a second, I only have the even powers in cosine x, whereas for sine, I only had the odd powers. Right? But other than that, they look like the same form, right? And this is just straight from the Mclaren series. Okay, so I have to do one more thing. I want to work out the algebra of this imaginary unit, right? So square root of minus 1. It's not a real number, but I treat it as just a symbol that has the property that when I square it, I get minus 1. Well, what happens when I cube it? Well, when I cube it, that's really the same thing as I times I squared, right? But I squared is minus 1, so this is really minus I. Right, so I is just I. It's just square root of minus 1, so we just call that I. I squared is minus 1. I cubed is minus I to the fourth is I squared squared, which is minus 1 squared, which is 1. What about I to the fifth? I to the fifth is I to the fourth times I. But I to the fourth is 1. So this is just I. And the cycle repeats again. Okay, so writing that out where I haven't done any of the computation here, right? So I is itself. I squared is minus 1. I cubed is minus I. I to the fourth is 1. And I to the fifth is I. And it starts over there, right? I to the sixth is minus 1. I to the seventh is minus I, and so on. So when you raise I to these powers, you get one of four possibilities. You get I, you get minus 1, you get minus I, or you get 1. Those are the four possibilities, and they just endlessly repeat, right, as I keep exponentiating I. Okay. Now, why did I want to talk about that? Because here's my idea. So my idea is plug IX, so plug IX into e to the x. What do I get? So the e to the x that I want to use is the Mclaren series for e to the x. This thing. So what do I get? I get that e to the x is equal to 1 plus ix over 1 times x to the first. Right? This is over 1 factorial if you like. Plus ix squared over 2 factorial, x squared. Plus ix cubed over 3 factorial, x cubed, plus ix to the fourth over 4 factorial, x to the fourth, and plus we'll do ix to the fifth over 5 factorial, x to the fifth, and so on. So I'm plugging in, sorry, this is e to the ix, I should say. Okay, so I'm plugging in ix here. Now, forget that, maybe never in your life have you plugged a complex number into a real function's variable slot. We're just doing this purely formally, right? So when we do that, I should say, I don't know why I keep writing the x here. I shouldn't have done that. I don't know why I was writing the x term. This is really what I get. Yeah, that's confusing. So why was I doing that? That's not at all what I get. So this is what I get. Okay. All right. So so then what is this? Let's just go piece by piece. Well, all I need to know are the powers of I. So I squared is minus 1. So I get a minus x squared over 2 factorial there. So I get 1 plus ix over 1 factorial minus x squared over 2 factorial. Plus, what's I cubed? I cubed is minus I, so this is minus, this plus becomes a minus I times x cubed over 3 factorial, plus I to the fourth, but that's 1. So this is plus x to the fourth over 4 factorial. I to the fifth is I again, so this is plus I x to the fifth over 5 factorial, and so on. What is this? Well, here's the expansion for sine, here's the expansion for cosine, and here is what I end up with. Where do the i's show up? They're on the odd powers, right? They're on first power, the third power, the fifth power, the seventh power, and so on. What shows up on the even powers? 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. If I did this again, it would be minus x to the 6 over 6 factorial. What am I reading off on the even terms? If I just circle the even terms here, what do I have? What is that? That's cosine x. All right, that's this expansion of cosine x. What if I circle the odd terms? Well, that's the odd terms. They have this extra I on them, but ignoring the I, it just is, look, the minus sign even matches up. It's sine x, right? So it's sine x, but I've multiplied this stupid I outside, so this is I sine x. And so what did we just show? We showed that e to the ix is equal to cosine x plus I sine x. And this is Euler's formula, which leads to what is called typically like the most beautiful formula in all of math, which I will show you now. So what is e to the I pi? Well, this is cosine of pi plus I sine of pi. But cosine of pi is minus 1 and sine of pi is 0. So this is minus 1 plus I times 0. So that's just minus 1. So e to the I pi is equal to minus 1. Or, another way you'll see this written, e to the I pi plus 1 is equal to 0. This is typically what is referred to as Euler's formula. So I know I wrote Euler's formula for the previous thing, and that is also true, but this is the special instance of plugging in pi here. So this is Euler's formula that, you know, is referenced a lot of times as the most beautiful formula in math. A lot of people, even physicists, say, you know, this is not just math. This is like the most beautiful formula, period. Of course, that's entirely subjective, but the reason why people like it is it's a single equation that relates 5 fundamental numbers, right? E, the imaginary unit, I, pi, 1, and 0, right? These are 5 like fundamental constants that obviously are very important in math, right? You have additive identity, multiplicative identity, pi, e, and the imaginary unit. So this is important stuff. So this is a very famous formula, and you'll encounter this a lot in any kind of discussion on like beauty in math and science. So I think I'll stop there for now, but I'll do a couple more of Euler's contributions next time. And then we will move on to the selected topics based on the poll. I will kind of be moving quickly, just trying to pick out the most interesting things that I think you guys will enjoy hearing about. So I think that's the plan. I'll post the homework. I'll post your next homework soon. Like I said, it'll be kind of like just asking you some questions and to write a bit about some of these mathematicians we've covered since I think the previous bookend was Thabit Evenkura. So so it will be picking up from there. Might go through the early 1600s. Might stop with like Descartes or something. And then the very last homework you'll have due like near the end of the semester will be one more kind of finishing us out, probably ending at Euler, or maybe some of the stuff I talk about next, depends on exactly what I cover. But anyway, I'll let you all know about all of that. So anyway, I will see you all on Wednesday.